Greeting to you all. My name is Malik and I am from Computer Science of Engineering Department E section. I am here to display my Tecktalk topic on the subject of design and analysis of algorithms. The topic name is going to be graphs, convolutions and neural networks, from graph filters to graph neural networks. Let's begin. Introduction. Many real-world data structures cannot be represented effectively using traditional grid-based formats such as images or sequences. Examples include social networks, citation networks, molecular structures, and transportation systems. These data types are naturally represented as graphs. This presentation explores how convolutional and neural networks concepts are extending to graph structured data, leading from graph filters to graph neural networks. GWNS. What are graphs? A graph is a mathematical structure consisting of nodes and edges. Nodes represent entities, edges represent relationships between entities. Graph can be directed or undirected and may contain weighted or unweighted edges. Their flexible structure make them suitable for modeling complex relationships. Challenges of learning on graph. Traditional machine learning models assume data lies on a regular structure such as grid or sequence. Graphs, however, are irregular and unordered. Key challenges include variable number of neighbors per node, no fixed spatial locality, permutation invariance. These challenges require specialized learning techniques. Convolution in traditional neural networking. In conventional neural networking, convolution operates on regular grids such as images. Convolution applies a shade filter across the input, captures local patterns, enable parameters, sharing, and translation invariance. Extending these ideas to graph is non-trivial due to their irregular structure. Graph signal processing. Graph signal processing provide a foundation for defining convolution on graph. In this framework, a signal is defined on the nodes of a graph. The graph structure influences signal behavior. Graph signals processing enables filtering and transformation of node features using graph topology. Graph filters. Graph filters generalize classical signal filters to graph structured data. They operate by aggregating information from neighboring nodes using the graph adjacency or Laplacian matrix, controlling the range of information propagation. Graph filters form the basic of early graph-based learning methods. Spectral graph convolution. Spectral method defines convolution using the graph Laplacian eigen decomposition. Key ideas include transforming signals into the graph spectral domain, applying filters in the frequency domain, transforming back to the node domain, while mathematically elegant. Spectral methods are computational expensive. Limitations of spectral methods. Spectral graph convolution faces several challenges: high computational cost, poor scalability to large graph, dependency on a fixed graph structure, limited generalization across graph. These limitations motivated the development of alternative approach. Spatial graph convolution. Spatial methods define convolution directly in the graph domain. They involve aggregation features from neighboring nodes, applying learnable weight functions, operating locally in the graph's structure. Spatial methods are more intuitive and scalable than spectral approaches. From graph filters to graph neural networks. Graph neural network extend graph filters by introducing learnable parameters and deep architecture. Key features include layer-wise neighborhood aggregation, nonlinear transformation, end-to-end learning, GNNs combine graph structure with neural networking learning capabilities. Graph neural network architecture. A typical GNN layer performs the following steps: collect information from neighboring nodes, aggregate neighbor features, apply a transformation and activation functions, update node representation. Stacking multiple layers enables learning from larger graph neighborhoods. Popular graph neural networking models. Several GNN architectures have been proposed, including Graph Convolutional Network (GCN), Graph Attention Network (GAT), Graph Sage. Each model differs in how it aggregates and weights neighbor information. Application of graph neural networks. GNN are widely used across various domains: social networks, analysis, recommendation systems, molecular property predictions, knowledge graph. Their ability to model relationships make them highly effective. Challenges in graph neural networks. Despite their success, GNN face several challenges: over smoothing in deep architecture, scalability to large graph, high memory and computation requirement. Addressing these challenges in an active area of research. Future scope. Future research in graph learning focuses on scalable GNN architecture, dynamic and temporal graph, explainable graph neural network, integration with other deep learning models. This direction aims to broaden GWN application applicability. Conclusion: graph provide a powerful representation for complex structured graph by extending convolution from grid to graph. Researchers have developed graph filters and graph neural networking. GWN combine graph structure with deep learning, enabling effective learning on relational data and opening new possibilities across many application domains. Thank you.